for the morning session is, so let me just share my screen. So it's coming. Yes, it's there. So our next speaker is going to be Dr. Mahidhar Tatineni. And he will be giving a talk on experiences with MVAPICH2 deployment on SDSC's Expanse supercomputer. So Dr. Mahidhar Tatineni received his PhD and MS in aerospace engineering from UCLA. He leads the user services group at SDSC. He's led the support of HPC and data application software on several NSF and UC University of California resources, including Expanse, Comet, and Gordon at SDSC. He's been involved in many NSF-funded optimization and parallel computing research projects. Most notably, he's also a co-PI on the Expanse HPC system and the National Research Platform projects at SDSC. So with this, I hand this over to Mahidhar. Mahi, are you there?
Thanks. Yeah, you can hear me okay?
I can hear you okay, yes. Can you
All right, let me start sharing my screen. Full screen on that. Okay. So the slides look okay?
Slides look okay, yes.
Okay, great. So I'll get started then. Okay. So yeah, today I'm just going to talk about the MVAPICH2 deployment on SDSC's Expanse supercomputer. Dr. Panda's group has been very helpful in optimizing and testing on the machine, and we've started to move applications to use MVAPICH2. So I'm going to go over some of the results of the benchmarks and where we are going. So just to start off, just a quick introduction on the history at SDSC. I think if you've been coming to MUG, you've probably seen this slide grow over the years. So we started long ago with Trestles in 2011 with MVAPICH2 on that machine, going to Gordon, which had 2 different lives. Just got retired actually. It was a dual rail QDR in IV, and I think that was the first dual rail implementation with Taurus support, and that worked really well on Gordon. And then on to Comet, which also just got retired from NSF service, but it's going to continue computing for the CW3 center, which was a Haswell cluster, and we had all flavors of MVAPICH on that, MVAPICH2, MVAPICH2X, GDR, and I think even the virtual cluster instance had a version. And our current system is Expanse. It went into production in December, and I'm going to go into the details of the system a little bit later, but it's basically AMD CPUs and HDR interconnect. And we have MVAPICH2 installed, and we are testing MVAPICH2 GDR, the latest version now, and more coming there. So the project itself, Expanse, is NSF-funded machine. It was a capacity system award, and basically the PI on the project is Professor Mike Norman, and then Dr. Altinters, Dr. Majumdar, myself, and Sean are the co-PIs on the project. The vendor was Dell, vendor's Dell, and we have storage from Aeon for the Lustre files. So this figure is basically right out of our proposal, but this was what was initially set up. So that's 13 scalable units, and I'm going to talk about the scalable units a little bit later, with 728 compute nodes and 52 GPU nodes. And all this changes in the next slide, so that's why I'm saying it's an initial setup. And then we had 12 petabytes of Lustre storage, and we're going to bring up a Ceph-based storage also a little bit later. And it really builds on Comet, which was aimed at the long tail science with lots of various application areas, pretty diverse application areas. And we've added a few tweaks in terms of operational innovations, like looking into cloud bursting and also looking into composable systems. So the system itself, the original system, as NSF funded, as I mentioned, was 728 nodes with about 93,000 cores and 52 GPU nodes with B100 GPUs. We just added an industry rack with 56 two-socket nodes. It's basically the identical scalable unit and 4 more GPU nodes. And very soon we'll be adding 2 more racks of, or I shouldn't say very soon, but when funding becomes available and when we get through the whole setup, we should be adding 2 more racks with AMD Milan-based nodes and A100 GPUs. So that should be coming later. And overall, like based on whatever benchmarking we've done, we've easily doubled the Comet throughput, and it's been a pretty smooth transition for anyone who's been going from Intel to AMD processors, and we've pretty much replicated the Comet stack on Expanse. It's been in production since December 2020, and it will have operations for 5 years. So a little bit on the system architecture. So it's built out of scalable compute units. And I'll go into the network at the rack level in the next slide. But basically, you have now with the addition of the new rack, now it's 784 nodes, so about 100,000 cores. And it's HDR 100 to the nodes and HDR 200 switches on top of the rack. And we can talk about that a little bit later. And then I talked about the Ceph and Lustre storage. We also have node local NVMe. It's 1 terabyte on the compute nodes and 1.6 terabytes on the GPU nodes. So that's kind of the structure of the system. So now, basically each SCCU has 56 CPU nodes, as I mentioned. That works out to 7,168 cores. And it's 1 HDR top of the rack switch with 40 ports. So we are splitting the 200 gigs into 40 200 gig ports into 80, basically 100 gig. So you get 60 links going into the switch, into the local nodes, and 200 links, 20 links going up. So it's a 3:1 oversubscription going between racks. So that's a pretty large chunk of cores on a single rack, and we should be able to do pretty good stuff even with a single rack setup. The nodes have 256 gigs of RAM each. And they're EPIC 7742 processors, so 2.25 gigahertz, and Zen 2 cores. And the GPU nodes have 4 and V100 GPUs and with 32 gigs of memory, 1.6 terabytes of NVMe, and also they have NVLink. And I have some benchmarks kind of showing what happens with that. I think I talked about this already from a switching perspective as well. And all of this connects out to our wider network, both through the data mover nodes and through Arista switches. So you can get to 100 gig connectivity to CNIC and 20 gigs into Exceed. We also have some direct connect options into Amazon, so which we will be using for cloud bursting testing. So the EPIC processor itself, you've probably all seen this, but I just want to go over it a little bit again. It's basically each chip has 8 core complex dies, and these CCDs connect to memory IO and each other through the IO die. And there are 8 memory channels per socket. With we have DDR4 memory at 3.2 gigahertz. And these can be abstracted into separate quadrants with 2 DIMM channels and 32 IO lanes. And then in each of the CCDs, there are 2 core complexes. with 4 Zen 2 cores in each CCX, which share a 16 meg L3 cache. So as I mentioned, you can split this up into logical quadrants. So you can have different NUMA domains. So on Expanse, we run with NPS4, which is 4 NUMA domains per socket. So you end up with 8 NUMA domains on a node. So yeah, if the memory is interleaved on the 2 memory channels, and the PCIe devices will be local to one of the 4 NUMA domains. And this is a typical HPC configuration, as most of our workload can be, is NUMA aware, and we can pin tasks appropriately and make use of the setup in an efficient way. So in terms of software stack, we have a pretty broad application base with installs and modules for most of the commonly used packages in bioinformatics, molecular dynamics, machine learning, quantum chemistry, structural mechanics, waves, and all kinds of math libraries. We, as I mentioned, have replicated most of the application stack from Comet on Expanse. And we've done primarily SPAC-based installs. So this is a change for us. We used to do ROX-based installs on Comet. So it's basically been all moved into SPAC on Expanse for the most part. And we are actively engaged with AMD under the HPC user forum activities to help with developing these SPAC recipes and providing feedback. And AMD has been very good in putting out their optimal versions of the SPAC packages, both on their website and pushing it out to the main repo. And yeah, I mean, anyone with AMD processors, you're welcome to join the forum and get involved in this activity. So I think it has a pretty broad impact once it gets back into the main SPAC repo. We'll continue to support singularity-based containerization on Expanse, just like we did on Comet. So in terms of benchmarks, just for acceptance, we did a lot of benchmarks last year and early this year, basically benchmarking CPU applications like GROMACS, NAND, Neuron, OpenFOAM, Quantum Espresso, Rxml, WRF, and Astral. So these are like a very broad range of domains, as you can see. And it's all kinds of codes: pure MPI, hybrid MPI, OpenMP, hybrid MPI, P-threads. And we've also kind of tried out all different compilers on Expanse. And it's been interesting. It's been, depending on the code, we've found different combinations have worked well. So it's not been a single compiler to pick, essentially, so far. Although the AOCC builds are now getting pretty good with the AMD optimization. So, so that's going to be a moving thing, I think. What's going to happen most likely is more refreshes on the software stack in the early years to kind of keep these going. As I mentioned, results on Expanse show pretty good performance compared to Comet. Depending on the code, we are able to match on a per core basis, or even go up to as much as 1.8x faster on a per core basis compared to Comet. You have to remember the memory bandwidth per core is actually slightly lower, but it's worked out pretty well in terms of performance. The overall memory bandwidth is much higher on the node, of course. The overall throughput, is easily going to be more than 2x, even though we have 2x the cores, and performance on average is about 1.4x on the application. Similar thing on the GPU side. We've benchmarked several applications like NAMD, Amber, TensorFlow, and lots of machine learning cases, basically. And we see about a 1.5x per GPU improvement over the P100 node. But depending on the code, this could be a lot higher. So, for example, Amber might be a lot better in that case. So that's kind of what we've tested. so there was a recent release of MVAPICH2 236. So we've been kind of benchmarking, and some of us are on the development projects along with Dr. Pranda's group. So we've been benchmarking some of the optimizations that his group has made with MVAPICH 236. So I'll go over some very early results basically. So first thing we did is run some of the collective benchmarks to see if anything major changed with going from 234 to 236. And this is just a 2-node case. And so on the top end, we didn't see much of a difference, but for the lower message sizes, there was definitely about a 5 to 10% increase in performance. And with the larger node count, I'm sure this will be a little bit better. So similar thing with OSU bcast benchmark. So the broadcast benchmark, you can see quite a bit of improvement at the low message sizes, going from 234 to 236. So 234 was right when we installed Expanse, and I think a lot of the optimizations weren't in there yet. And so you can see nice improvement basically going forward. So I went back and reran some of the Rxml and Neuron benchmarks that we had done before with either Intel compilers, Intel MPI, or with older versions of MVAPICH. So this is Rxml is a genomics code, basically 208 tax, 18 tax, 2294 DNA characters test case, runs for like 100 bootstraps. And this is an MPI plus pthreads code. And so here I'm just adding the column from that I recently did with Intel compiler and MVAPICH2 236. So it's been a huge improvement going from, and I don't know how much of this is from MPI or, and if something else has changed also, but it's been pretty good. Like, I mean, if you look at the and these are all single node, even single socket runs actually. And one of the things I've shown below is we did make sure to bind so that we didn't get like extra memory bandwidth by picking up 2 different sockets with more memory channels. So we were binding compactly in the setup for this MPI plus pthreads test. So you can see the snapshot from HTOP below for both the 30, I think 20 core case and a 40 core case. So the way we do this is we lay out the processes, MPI processes using binding flags, and also for the pthreads, we were using task set to kind of make sure that they were landing where we wanted them. So so with that, you can see quite a huge improvement over Comet. Partly this is a little tough to measure because we have a way more memory channels per socket. So even if I bind everything to the first 2 memory channels, it still might be a little bit better memory bandwidth compared to Comet. But still, we get pretty good performance even going out to 40 threads compared to Comet. So it's more than 2x improvement in this case. So you've gone from, so the Expanse dev was about a year and a half ago, I think, or it might be even more than that. It was a Expanse node, but it was with our development stack. I think this test was with Intel MPI, but I have to go back and double check. But you can see we've improved quite a bit going between the two runs. Similar thing with Neuron, it's a large-scale model of olfactory bulb test case with 10,500 cells and 40,000 time steps. So I just wanted to first show you that we did have to be careful about picking how the tasks get laid out, because if you cheat and let it spread, like for the smaller core counts, you can pretty much get awesome numbers because you get so much more memory bandwidth. So all the tests we did, we were trying to keep it nice, keep it fair, basically. So again, we are comparing with, so the task counts are odd because Comet had 24 cores per node. So we are basically doing 4 nodes, 8 nodes, 16 and 32 on Comet. On Expanse, of course, we have almost 5x the core count. So it's a little fewer nodes. So we were trying to do per core as close as we could get. So 96 would be 2 nodes, and 192 that could be, is 96 one node, and 192 would be 2. 384 is 3 nodes, and 768 is basically 6 nodes. So it is densely put into the layout wise. So if you look at Expanse numbers from, so we have, for this, we have Comet numbers. We had a AMD test cluster before we actually deployed Expanse, where I was running with Intel, and then with MVAPICH 2235, and then now with MVAPICH 2236. So at the smaller core counts, we didn't see much difference, but as you went to the larger core counts, you can actually see, and this is very repeatable. We did lots of simulations and average the time. So you can see a pretty significant improvement going from 235 to 236. And now this time is actually faster than the Intel MPI time. Let me see how much time do I have. Okay. Yeah. So the next thing I want to go into is MVAPICH2 GDR results. And I have the Comet P100 architecture here just to show you what changed between Comet and Expanse. So on Comet, we had 2 GPUs per socket, and but as you can see, going between the sockets, you had to go through the host, and that will have performance implications, and I will show you that. On Expanse, if you look at the same topology information, you have basically NVLink between all the GPUs. So the first thing I decided to test was basically look at, like, how do we do compare in the intranode test, right? So if you look at the P100 results, there was actually quite a bit of variation between, like, GPUs on the same socket and GPUs off socket. And I think there is something, I'm guessing I had one of these plots is probably not accurate labeling. But anyway, there was a wide variation. This is because of the host being in the way when you go between sockets. So now with Expanse, with the NVLink, we don't have that issue, and the latency is much lower between GPUs, and also it doesn't matter if I'm picking GPUs on the same socket or on the different socket. So that's a nice improvement. Similar thing with OSU bandwidth benchmark intranode. If you looked at the Comet results on the left, the bandwidth kind of is identical if the GPUs are on the same socket. So 0 and 1 were on the same socket, and 2 and 3 were on the same socket. So you kind of get a nice curve there. But going off socket, it got cut off quite a bit. Now with Expanse, there's like no difference basically between the two curves. So that's and you can see this is because it's I mean, faster GPUs and faster memory. The bandwidth is also pretty good going up. So so we are actually testing some applications like HumDBlue and a few others using the MVAPICH2 GDR. This is really new installation, so I haven't had chance to test too many applications, and we'll have results soon, I think. So that's, but I can already see that there's it's a nice improvement over Comet given the architecture. So overall, I think Expanse should provide a huge increase in performance and throughput. The machine's already running full, so we are and we'll be adding 2 racks in a little bit, so that hopefully will help with some more of the load. And there's two sets of racks, basically the NSF funded racks, which is basically the 13 original racks with 728, compute nodes and 52 GPU nodes, and then the industry rack that just got added. And we have HDR InfiniBand going, and 100 to the nodes and 200 switches on the top of the rack. And MVAPICH 236 early results, it looks like there is improvements in performance for a lot of the benchmarks and applications. So we'll do a lot more testing, of course, with this. And similar thing with MVAPICH 2 GDR. And you can follow all things Expanse at expanse.sdsc.edu. Thanks. And let me go to the final slide, which has all the people who are involved with the project. It's never simple. So I think I can stop there and take questions if there are any.
Right. So thank you very much for your talk. So let me see. Right. So I have a few questions. Do you have any recommendations for compiler on the Expanse system for applications in general?
Yeah, so it's been pretty much a moving target. For example, when we started out, the older AOCC compiler was running slower than both GCC and Intel. Now, I think with some applications, like we just recently tested CP2K, for example. Actually, the AOCC compiler is doing better now. So we kind of have to keep revisiting it, I think, at least for the first year or so, because it's changing quite a lot. AMD is putting in a lot of work into the AOCC and AOCL libraries. So that kind of is the reason for the improvements there. So what I would have found is it's very application dependent. Some applications still do better with Intel. For example, WASP still does better with Intel. There's some applications that are like Rxml, I think, is a good one, where Intel compiler does better than everything else. And then for some, GCC 10 works fine with the ZN version 2 flags. Is better than Intel some cases. And Intel MKL, depending on the routine that you're calling, it may or may not be faster. So again, we have to kind of check your own application. So in our early user period, we had users try all different kinds of things, and we found that they found different compilers for different applications. So, but I would think in the long run, AOCC will start getting to be the default, but it might take some time.
Okay. So are there any recommended performance profiling tools on Expanse?
Oh yeah, so I didn't talk about it. There is a UProf, which is from AMD for the for basically the node level performance. So I think you can use it with MPI too, but I haven't really tested it that way, I think. But but UProf is a good tool. PAPI, as far as I know, doesn't have all the, it's not at least right. I mean, I have to check if there's a newer version, but when I checked last, it didn't pick up all the AMD counters, I think. So.
Okay.
So I think UProf is probably the best bet. I don't think it has an API for you to build it into like MPI or some other tool, but
okay.
That's what things are. But I think other than that, we have Tau installed, and we have the traditional profiling, like we can do even, I think we have DDT with the limited license, so you can use that also for profiling.
Okay, sure. Excellent. Thank you. One last question. So the numbers that you were presenting, there were some result from the dev partition and some from the Expanse.
Yeah.
The production, I think. So
yeah.
There was difference in performance. Is this because the compute nodes are different or something else is different?
So a lot of things are different, right? So the dev partition, I think, was an identical node, except that that was the really early stack, and like we were just trying out our application stack.
Okay.
So it probably didn't have all the optimizations that kind of you've been putting in with flags and other things. also your MVAPICH, when I think we tested that there, all the MPIs were also not aware of the AMD architecture, I think. So it was a little different.
Okay.
So some of that improvement might have come from there, I think. It's difficult to do, to check because the machine's gone, the dev machine. So I can't go back and rerun it with the same identical stuff.
Okay.
So that's why what I was trying to do was to run with 234 and 236 on the same hardware.
Right. Okay. So thanks a lot, Mahidhar, once again. Excellent talk. So with this, we conclude our morning session. So we have a 30 minutes break. So we'll actually resume MUG at 1:30 p.m. Eastern time. So thank you to all the speakers and attendees so far. So look forward to seeing you at 1:30.
Thanks, everyone.
Thanks.